Good afternoon. So in this lesson, we're going to learn another application of the Riemann integral, namely the finding of the length of a curve. So a curve given by a function, either a function of x or a function of y. The formula will be very similar. So this is yet another application of the Riemann integral, together with the applications we know already, like the volume of revolution, which you learned before. There will be another application after this, which is the finding of the surface area of a revolution. And the approach is very similar like the one we used for the volume of revolution. So I'm gonna go over the approach a little bit faster, not faster, I mean in a more streamlined way, so that we move to the formula quickly, because the idea is really the same. What you do, you make a partition of the interval. So take a moment to write down or sketch this graph. Let's say this is a generic function of x between a and b. The whole idea is to produce a Riemann sum that will approximate the length of the curve. And then when we take the limit as n goes to infinity, by n meaning the number of points in the partition, then we arrive to an integral that will give us hopefully the length of the curve, if that's our goal here. So it's important to remember that when you take the limit of a Riemann sum, so when you pick a Riemann sum, let's say with a partition x naught, x1 up to xn, you have a typical interval in the partition, xi minus 1 xi. Typically we denote by delta x, right, the distance between any two nearby points on the partition. As we take the limit of the Riemann sums as n goes to infinity, this interval delta x becomes tiny and is denoted by dx. And that's the notation when you have the limit of the Riemann sum. That dx essentially replaces delta x. You can also think of this dx as a small change in x, in the limit. And so that's the part that becomes part of the integral. I mean, the delta x and becomes dx, and then of course the rest of it comes from whatever we want to compute. In the case of volumes of revolution, everything else was basically denoting a volume of a slice or a shell. Dx was part of that volume, right? I mean, dx used to be the height or the width of, or radius maybe of part of the radius, for example, of a shell, and so on and so forth. Here we're going to do the same thing with the aim to actually approximate, like I said, the length of the curve. So when we come up with this partition, we want to basically approximate the length of the curve with a straight segment. So if you imagine here on the graph, let's say you pick a point x, a generic point x between a and b, and you take the nearby point x plus dx. So if you have dx, a small change in x, a nearby point is x plus dx. So dx will be the distance between x and x plus dx. And when I raise a perpendicular over x plus dx, I'm going to basically make a tiny right triangle here, whose hypotenuse will approximate the length of the curve. So to be really clear on what we're trying to do here, I'm going to basically sketch this little triangle separately and by an exaggerated size. So imagine you zoom in that little piece. What you should see there basically is a right triangle with this side being of length dx, right, because it's the change between x and x plus dx. And the corresponding vertical side will be the change in the y coordinate. If you go back to the to the original graph here, for a small change in x, you're going to have a small change in y coordinate, from y to y plus dy, if you want, here on the left side. So dy will be the change in y corresponding to a small change in x. And the hypotenuse of this little triangle is going to be a piece of the curve. So that's basically the piece of the curve whose length you try to approximate. So you're going to basically replace the length of the curve with the length of this hypotenuse. And of course, if dx and dy are very, very tiny, then in the limit, these hypotenuses that will, add up via the integration to the whole curve will basically give you the length of the curve. So what we integrate basically is over the length of this side, the hypotenuse. The only thing is to just write that in terms of either x or y. At this point, I want you to remember that we have a formula for the differential. So if you have a function of x, y equals f of x, dy is the differential of f, which is equal to f prime of x dx. So from Pythagorean theorem, this side that we're going to integrate over, so the hypotenuse, is going to be the square root of dx, well, let's start with dy first. So dy squared plus dx squared, and dy is going to be f prime of x dx quantity squared plus dx squared. And if I pull out dx squared, so if I pull out dx squared, I'm going to end up with 1 plus f prime of x squared. And I can move dx outside the radical, and you end up with 1 plus f prime of x squared under the radical with dx on the outside. So this is basically the stuff to integrate, which will give you eventually the length of the curve. So the stuff to integrate basically comes from Pythagorean theorem, because when you make that partition, the length of the curve, which you try to approximate, comes from the hypotenuse of that right triangle. And so without further ado, let's write down the formula for the arc length. So the arc length of the function y equals f of x for x between a and b is going to be, let's denote that by L, is going to be the integral from a to b of square root of 1 plus f prime of x squared dx. The same type of discussion can be made if the function is with respect to y. So I'm not going to, of course, go over this one more time. So let's write it like or, right? If you have a function with respect to y, it's really the same idea, except that you have an integral in y. So if x is a function of y, and let's say y is between c and d, then the arc length will be the integral from c to d square root of 1 plus f prime of y squared dy. In some sense, things are kind of easier on this lesson, because most of the time we don't even have to sketch actually the function to apply the formula. We don't need to visualize much. We don't need to come up with points of intersections, or, I mean, once we know that the curve is given by the graph of a function between 2 points like that, we just basically integrate it according to this formula. The only thing to do is to make sure you compute the part that you have to integrate carefully and make all the simplification necessary. That's sometimes a little bit tricky, as you will see in some examples. And we're going to do that on the second page. Actually, before I do that, because we're going to need it for the examples, I want you to remember the one of the formulas we're going to need, okay, for the next examples. So the semi-sum, the square of this, the binomial. So a plus minus b squared is a squared plus minus 2ab plus b squared. We're going to need this formula because we will need to simplify these radicals. So often we're going to end up with quantities like this, and we will have to basically write those quantities in form of a square. So we're going to have to basically complete the square, right, before integration. because otherwise we can't get rid of the radical. So there is a class of problems that basically lead to this formula. And so we're going to do a bunch of them, and then you'll have some of them as a homework. So stay tuned for the second page. All right, so our first example, let's say we want to find the length of the function y equals x squared over 4 minus 1/2 natural log of x with x between 1 and 2. Now, obviously, the problems that have to be done by hand are in such a way that that formula, that radical, can be simplified. So let's write down the formula one more time here for the length of the curve, so we can follow it. And it's f here, f prime of x squared. So let's do the derivative. So we're going to basically have to come up with, so the function is going to be x squared over 4 minus 1/2 ln of x. We need the derivative. By the way, in some cases you can write the formula by replacing f prime with dy dx. Is the same thing, obviously. And if it was a function of y, it would be dx dy. So that's another notation for the derivative. So we need f prime first. Make sure you don't rush, because many people plug in just the function and forget about that. There's an entire computation to be made here, right? We need the derivative, we need to square it, we need to add 1, and then take the radical. So we need to do quite a lot of algebra before we actually get to the integral itself. So f prime of x becomes 1/4 times 2x minus 1/2 times 1 over x. So that's going to be x over 2 minus 1 over 2x. Then we need to square this. So f prime of x squared becomes quantity x over 2 minus 1 over 2x squared. And then add 1. Okay, I mean, we could add 1 later or now, but let's do actually one step at a time, because I want you to just look carefully at what happens here. So with the algebra. So let's apply the formula that I mentioned on the previous page. So that's x over 2 quantity squared minus 2 times x over 2 times 1 over 2x plus 1 over 2x quantity squared. Don't rush to simplify this. Just pay attention to the middle term. So purposely, I'm not going to simplify this completely, because I want you to see what happens when I add 1. So that's just f prime squared. And notice that the middle term simplifies to 1 over 2, right? Because x cancels, 2 cancels. And so that's going to be minus 1 over 2 plus 1 over 2x quantity squared. On the other hand, what you have to integrate is 1 plus f prime squared under the radical. So at this point, let's add 1, the 1 from the formula. And notice that 1 can be combined with the existing minus 1/2. So the first 3 terms are f prime squared. Then you add 1. And when you combine these guys, it becomes x over 2 squared plus 1 over 2 plus 1 over 2x squared. All right, so this is the little trick for problems like this that sometimes is frustrating, but slow down a little bit, catch up with the computation, and follow closely what I'm going to do here. Notice that precisely the same expression with minus 1/2 stood for x over 2 minus 1 over 2x squared. Okay, so over here you had basically an example of the formula a minus b squared, a squared minus 2ab plus b squared. What you end up with here when you add, after you add up 1, this involves the same terms except there's plus in the middle, right? So basically you have the same expression but with plus 2ab rather than minus 2ab. which of course based on a same formula recombines into a plus b squared. This is your goal because you're going to have to take the square root of that. So this plus 1 over 2 is just right to recombine this into a square. You can again view 1 over 2 as coming from 2 times x over 2 times 1 over 2x. It's just with plus between them. So obviously without this little trick we cannot basically simplify this. I mean, the problem is constructed so that it's simplified in this manner. So then 1 plus f prime therefore recombines into x over 2 plus 1 over 2x squared. So one more time, 1 plus f prime squared is essentially x over 2 plus 1 over 2x quantity squared. And now we can proceed with finding the length of the curve. So the interval of integration is 1, 2. Formula is square root of 1 plus f prime of x squared, which it's simplified into x over 2 plus 1 over 2x squared. That allows me to simplify the square root with the radical. And now it should be a simple integral, term by term, right? So the first one is 1/2 x squared over 2 plus 1 over 2 ln of x between 1 and 2. Four over 4 plus 1/2 ln of 2 minus 1 over 4 plus 1 over 2 ln of 1, which is 0. 4 over 4 is 1, ln of 2 over 2 minus 1 over 4, ln of 1 is 0. So this ends up being 3 over 4 plus ln of 2 over 2. All right, so the problems in the homework, most of them are similar to this. Kind of all of them have this type of simplification. Let's do one more, this time involving a function of y. And you'll see that pretty much all of them, I mean, all of these problems of this type will basically have that little trick with minus 1/2, which becomes plus 1/2 after you add 1. So let's see. Yeah, so let's say, suppose you have to find the length of x equals 1/3 square root of y, quantity y minus 3, with y between 1 and 9. So let's actually write this as a combination of powers. So that's going to be 1/3 y times y to the 1/2, that's y to the 3/2 minus y to the 1/2. So I'm writing it that way because we're going to have to prepare it for differentiation, right? So in this case, the formula will be the integral from 1 to 9 square root of 1 plus f of y, f prime of y squared, right? So like, or dx dy squared dy. Same formula, but in terms of y. And let's take separately the derivative. So let's simplify it completely before you plug it into the integral. So dx dy is 1/3 times 3 over 2 power rule there, y to the 3 over 2 minus 1, which is 1/2, minus 1/2 y to the minus 1/2. We cancel the 3. Let's square dx dy. So that's going to be 1/2 y to the 1/2 minus 1/2 y to the minus 1/2. And let's apply the formula just like before. So I think I'm going to write it from the left here. So it's going to be 1/2 y to the 1/2, don't simplify it yet, minus 2 1/2 y to the 1/2 times 1/2 y to the minus 1/2 plus 1/2 y to the minus 1/2 quantity squared. So I hope you know the drill for now. This will recombine into a square. Notice again, the key thing to notice what happens in the middle here. Y to the 1/2 with y to the minus 1/2 will cancel. When you multiply them, they become 1. 2 with 1/2. So the middle term becomes minus 1/2. And now when you add 1 to dx plus dy squared, so when you add 1 to this, the middle, the minus 1/2 becomes plus 1/2. So the same expression, but with plus 2ab, right? The same formula, which fortunately recombines into 1/2 y to the 1/2 plus 1/2 y to the minus 1/2 squared. And that allows me to compute the integral. So let's set up the integral, and I'm going to leave it as an exercise at the end. I'll give you the answer. So the length is going to be the integral from 1 to 9 square root of 1/2 y to the 1/2 plus 1/2 y to the minus 1/2 squared dy. These cancel, and you're left with 2 power rules. And the answer should be 32/3. So do this on your own and check to see that you get 32/3. So that's it for today, and I'll see you next time.